Welcome Tashians to Sleep By. Tonight, we drift into a story that begins far beyond our solar system. A story carried on the quiet path of an object that arrived from the deep interstellar dark. We'll explore a question that captured the imagination of scientists and sky watchers across the United States. Did the mysterious Object 3 Atlas trigger the strongest solar flare of 2025? In the soft calm of this hour, we'll let the cosmos speak slowly. We'll follow the gentle arcs of magnetic fields, the faint signatures of distant elements, and the soothing rhythm of scientific discovery. Settle in, breathe deeply, and let the universe unwind itself in a way meant only for quiet minds and restful hearts. In the quiet pre-dawn hours, when most of the United States still slept beneath a blanket of cool January air, a silent signal appeared in the data stream of the Atlas survey in Hawaii. It was the kind of moment astronomers know well, when something faint, something subtle, begins to whisper from the darkness. Atlas, designed to watch the skies for objects that wander too close to Earth, spends every night scanning for the unexpected. But on that particular morning, the unexpected had arrived from much farther away than anyone anticipated. A tiny point of light drifted across successive frames, barely distinguishable from the deep field of stars behind it. Nothing about it screamed importance. It didn't blaze like a comet, it didn't streak like a meteor, and it didn't behave like the hundreds of near-Earth asteroids the system catalogs each year. Instead, it carried the gentle, almost shy signature of something unbound to our sun. Something moving just slightly too fast, and at just the wrong angle to belong to the gravitational family we call home. The astronomers on duty logged the signal, tagged it for follow-up, and continued through the motions of a typical observation cycle. But as the sun began to rise over the observatory domes, and as morning cracked along the coastlines of the continental US, the automated tracking algorithms began to outline a trajectory that didn't make sense. The object's path wasn't elliptical or parabolic in the way cometary paths usually are. It was hyperbolic, open, sweeping, the mathematical equivalent of a visitor simply passing through. Within hours, observational teams in Arizona, New Mexico, and California pointed their instruments toward the coordinates provided by Atlas, hoping to catch the faint dot before daylight consumed the view. Slowly, frame by frame, the picture sharpened. The object was real. It was moving. And more importantly, it was moving too quickly to be gravitationally bound to our solar system. That realization carried a quiet weight, similar to what astronomers felt when Oumuamua in 2017 and Borisov in 2019 crossed our celestial doorstep. This would be the third time in recorded history that an object from another star system, or perhaps even from the drifting debris between stars, had wandered into the warmth of our sun's gravity. The designation came swiftly, 3I, the third interstellar object humankind had ever confirmed. And because Atlas had been the first to detect it, the second part of its name was already written. 3. Atlas slipped into the scientific record with the serenity of a calm tide rolling onto a quiet beach. But unlike the broad public attention that Oumuamua received, 3I Atlas entered the world quietly, almost privately. Noticed first by those who spend their nights immersed in data streams and spectral plots. For them, discovery is not fireworks or fanfare. It is a soft pulse in the darkness, a number on a screen, a realization that grows slowly like dawn light. As word spread to solar physicists, planetary scientists, and research teams across the US, the curiosity deepened. Interstellar objects carry with them the chemical fingerprints of distant places. They offer glimmers of what other solar systems might be like, what materials drift between the stars, and whether the processes that shaped our cosmic neighborhood are shared across the galaxy. Each one is a message, faint but meaningful, from somewhere unimaginably far away. As the weeks passed, astronomers continued to monitor 3I Atlas. It brightened slightly as it approached the sun, though not in the way typical comets do. Its emissions were sporadic, uneven, and puzzling. Some nights, its coma appeared stable, soft, and uniformly illuminated. Other nights, it flickered unpredictably, like a candle struggling against a breeze. Spectrographs captured unusual ratios of elements, hints of exotic ices, and signs of materials that may have been shaped not by a star like ours, but by something cooler, older, or more chaotic. Each observation brought new questions, and the scientists observing it, many working in US universities and research centers, felt the familiar thrill of encountering something beyond the standard models. There is a kind of quiet reverence in the scientific community whenever the universe hands us a rarity, something so infrequent that it may only appear once or twice in a lifetime. And so, as 3I Atlas drifted deeper into the inner solar system, it became the subject of late-night discussions in dimly lit labs, group emails sent between researchers who should have been sleeping, and impromptu Zoom meetings with scientists from different time zones trying to puzzle out the object's unusual behavior. Was it shedding material unevenly because of internal fractures? Was it rotating in a strange, tumbling motion that caused sunlight to strike its surface irregularly? Or was it composed of substances unfamiliar to comets born near young stars like ours? Then came the coincidence that ignited imaginations everywhere. Just days after 3 Atlas made its closest approach to the Sun, the solar surface erupted in one of the strongest flares of the entire 2025 solar maximum. The flare was enormous, powerful enough to trigger alerts across NOAA systems, powerful enough to light up auroras far deeper into the United States than usual, powerful enough to make the public pause and wonder whether this cosmic visitor had somehow disturbed the Sun. News outlets began to ask the question in headlines. Social media speculated in all directions. Even some amateur astronomers wondered quietly, half seriously, whether the timing was too close to be coincidence. Meanwhile, professional scientists maintained their calm, noting the statistical likelihood of overlapping events during a solar maximum, but still intrigued enough to look more closely at the exact timing and trajectory of 3I Atlas as it passed near the solar corona. The discovery, no matter how quietly it began, had now grown into a broader conversation, one that blended curiosity, scientific discipline, public wonder, and the timeless human tendency to draw connections in the cosmos. From the first faint detection in a Hawaiian sky to the flurry of analysis across the American scientific landscape, 3I Atlas had become more than a distant traveler. It had become a puzzle, a visitor, and a reminder of how vast the universe is and how little we truly know about what drifts between the stars. To understand the mystery of 3I Atlas, it helps to drift into the deeper question of what sets interstellar objects apart from the familiar wanderers of our own solar system. Most of the icy bodies we know, comets, dormant comets, asteroids shaped by ancient collisions, were born around the same sun that warms our skies. They formed from the swirling disk of dust and gas that encircled the young star billions of years ago, settling into orbits shaped by gravity, by time, and by countless interactions with other objects. These objects share a common ancestry. Their chemistry reflects the composition of the early solar nebula. Their movements trace the long, predictable paths laid down by our sun's gravitational pull. They belong to the family. Our stellar objects do not. They are cosmic travelers, unbound, unclaimed, and forged in places far beyond our reach. When one drifts into our solar system, it arrives with its own story, shaped by its own star or environment, carrying the scars of its own journey. And unlike the objects that loop around the sun in regular cycles, interstellar bodies approach on trajectories that are not circular or elliptical. They move on open, hyperbolic paths that reveal their freedom from our star's hold. This is often the first clue astronomers notice: the speed, the angle, the shape of the orbit, telling a quiet but unmistakable truth. The object has come from somewhere else entirely, but the differences go deeper than motion. They extend into the very matter that composes these celestial visitors. Solar system comets typically contain water ice, frozen carbon monoxide, methane, carbon dioxide, dust grains coated with organics, and fragments of material left over from the earliest days of our planetary neighborhood. Their chemical signatures, while varied, fit within a familiar pattern. When sunlight warms them and their ices vaporize, the gases they release follow predictable ratios. Their dust tails glow with expected colors. Their spectra show lines scientists have seen countless times before. Interstellar objects often refuse to fit these patterns. Oumuamua, the first interstellar object ever observed, offered no visible coma at all, confusing astronomers who expected it to behave like a comet but leave a faint streak of dust or gas behind. Instead, it tumbled strangely, accelerated slightly without explanation, and displayed no spectral features that matched the usual catalog. Less than 2 years later, Borisov, the second interstellar object, did exhibit a coma, but its composition suggested chemical environments that differed subtly from our own. It contained proportions of carbon monoxide far higher than typical solar system comets, hinting that it may have formed in a colder, more distant region than anything our sun ever experienced. And so, when 3I Atlas appeared, astronomers across the US and around the world immediately turned their attention to what made this visitor distinct. Its trajectory confirmed its interstellar origin, yet its behavior presented a blend of familiar and unfamiliar qualities. It released gases, as comets do, but not in a stable rhythm. Some nights, it brightened in sharp bursts, as though internal pressure pockets were releasing suddenly. Other nights, it faded almost completely, as if the sunlight struck surface materials that were not volatile at all. These fluctuations suggested complex layering, perhaps crusts of minerals beneath sheets of exotic ices, or fractured surfaces shaped by collisions in a distant star system. The composition of interstellar objects also reveals something profound. They carry microscopic clues of the environments where they form. Every icy grain, every trapped molecule, every dust particle is a fossil from another corner of the galaxy. Some may have formed in the cold outer regions of their parent systems, where temperatures drop so low that even nitrogen and oxygen freeze into ices. Others may have originated closer to their star, where heat sculpts minerals into different forms. Each interstellar visitor is a sample return mission delivered by nature, and because these objects travel for millions, sometimes billions of years through empty space, they accumulate the effects of cosmic rays, ultraviolet radiation, and collisions with tiny grains drifting between stars. These processes alter their surfaces in ways unlike anything seen on comets native to our solar system. Another difference lies in their rotation. Solar system comets often spin in somewhat predictable manners, their movements shaped by centuries of solar heating and gravitational interactions. Interstellar objects, having endured eons of unregulated forces, can spin erratically, tumble unpredictably, or rotate with unusual speeds. Their shapes can be elongated, flattened, or fragmented from past encounters we can only imagine. When 3I Atlas was observed, astronomers noticed subtle shifts in brightness that suggested an irregular rotation pattern. This meant the object might not be smoothly shaped. It could have ridges or asymmetrical contours that catch and release sunlight in staggered rhythms. There is also the matter of age. Interstellar objects are ancient, older than Earth, older than our sun, perhaps older than life itself. They may have been ejected from their home systems during planetary formation, flung outward by gravitational interactions, or dislodged by collisions with forming planets or wandering stars. Once cast into the void, they spend unimaginable spans of time drifting in near absolute cold, isolated from everything except the faint glow of the galaxy. When one finally crosses paths with our solar system, it brings with it the weight of that long cosmic journey. And yet, despite these differences, there is something strangely comforting about interstellar visitors. They remind us that our solar system is not an island. It is part of a vast cosmic ocean through which countless objects drift silently. Most pass through unnoticed. A few, like 3I Atlas, enter in just the right direction, at just the right speed, to be illuminated by our sun and observed by our instruments. Each one deepens our understanding of the galaxy, offering glimpses into the materials and processes that shaped worlds we will never see. For scientists in the US and beyond, interstellar objects embody both scientific rigor and a kind of poetic wonder. They are evidence that the galaxy is interconnected, that materials can travel from one star's cradle to another's doorstep, and that the processes shaping planets are not confined to any one place. When 3I Atlas was analyzed, every spectrum collected, every brightness curve recorded, every trajectory plotted, told another small part of the story, that this object was not like the comets we know, that it carried secrets of a place our species will never physically travel to, and that its arrival was a rare opportunity to study something forged in the disk of another star, possibly hundreds of light-years away as 3I Atlas drifted deeper into the inner regions of our solar system. Astronomers began to notice a series of behaviors that felt strangely inconsistent, almost like a visitor who couldn't decide how brightly it wished to reveal itself. The earliest observations showed a faint, steady glow, a soft halo of dust and gas that surrounded the object like a thin veil. At first, everything about it matched what scientists expected from an interstellar comet entering a warmer environment. Sunlight touched its icy surface, heated it gently, and released small plumes of vapor into the surrounding vacuum. But something shifted as it approached the sun, something subtle, something unusual enough to cause researchers to sit up a little straighter in quiet observatory rooms during late-night hours. On some nights, the object brightened dramatically, as if a sudden burst of energy had surged from its interior. This brightening wasn't gradual. It occurred in abrupt jumps, like a heartbeat quickened by a hidden stimulus. Then, just as quickly, the brightness would fade again, collapsing back to its earlier state. For astronomers accustomed to the quiet, predictable behavior of solar system comets, these fluctuations felt irregular, almost erratic. Some described the brightness curve as jittery, others called it restless. But beneath these informal words lay a deeper scientific curiosity. What was causing these changes? What mechanism inside 3I Atlas could be responsible for such uneven behavior? One possibility considered early on was rotational tumbling. Many interstellar objects spin in chaotic patterns, not neatly rotating around a single axis, but wobbling unpredictably, like a poorly balanced top. If 3I Atlas tumbled in this way, sunlight would heat different regions at different times. Some areas might contain volatile ices that vaporize quickly, while others could be covered in darker, more stable materials that remain dormant until sunlight reached them. This uneven heating could result in sudden jets of gas erupting from pockets on the surface, causing bursts of brightness captured by telescopes on Earth. To investigate this idea, teams in the US used time series photometry long sequences of brightness measurements to try to detect a rotational pattern. They found hints, but no firm answers. The light curve had rhythm, but it was irregular, as if the object continued changing its own pattern night by night. This inconsistency added to its mystery. Was the surface fracturing as it heated? Were new vents opening unexpectedly? Or was the object breaking apart internally in ways too subtle to detect directly? Adding to the puzzle were the changes in the shape and density of its coma. A coma is the cloud of gas and dust that surrounds a cometary nucleus, and most comas behave like expanding mist, soft, diffuse, and relatively even in brightness. But 3I Atlas displayed a coma that pulsed, thinned, thickened, and drifted in ways that hinted at intermittent activity. Images taken from observatories in Arizona showed the coma stretching slightly toward the sun one night, then spreading laterally the next night, as though jets from different parts of the nucleus were switching on and off. This kind of activity is rare in typical comets, but not impossible. In interstellar objects, however, it becomes a clue, a signal that the object's interior chemistry and structure may differ significantly from anything created near our sun. Spectroscopic observations added yet another layer to the intrigue. When scientists analyzed the light reflected and emitted by 3I Atlas, they expected to find the usual signatures of common cometary gases: water vapor, carbon monoxide, carbon dioxide, maybe nitrogen compounds or organic molecules. Instead, the spectral lines varied from night to night. Some nights showed stronger carbon emissions with weak water signatures. Other nights revealed unexpected molecular fragments that hinted at exotic ices or materials altered by millions of years of cosmic radiation. These shifts suggested that the object's surface wasn't uniform. Different patches contained different compositions, releasing different gases when heated. It was as if the object had collected layers of diverse materials during its long journey through the galaxy. Another clue came from the rate at which 3I Atlas was shedding material. Comets from our solar system typically lose mass in predictable amounts as they approach the Sun, forming tails that stretch gracefully across the sky. 3. Atlas did produce a tail, but it appeared inconsistent, narrow and faint one evening, broader and more pronounced the next. When astronomers modeled the dust particles within the tail, they found signs of fragmentation. Some of the dust grains were smaller than expected, almost powdered, as though the object had undergone mechanical stress or radiation damage over millions of years. That could mean the surface, when heated, released extremely fine dust in bursts rather than in smooth streams. The erratic brightening also sparked discussion about structural instability. Interstellar objects are often ancient, battered remnants of violent processes, collisions in their home star systems, gravitational ejections, planetary upheavals. These events can fracture an object internally, leaving it riddled with cracks and voids. When warmed by the Sun for the first time in perhaps billions of years, these voids might expand or rupture, creating sudden jets of gas that flare outward like tiny volcanic eruptions. These eruptions, invisible to the naked eye but glaringly obvious in telescope data, could explain the brief spikes in brightness recorded by observatories. As 3I Atlas drew closer to the Sun, these behaviors became even more pronounced. Some researchers wondered whether the object might partially disintegrate during perihelion, breaking into fragments the way comet Ison did years ago. Though 3I Atlas did not fully break apart, subtle changes in its brightness distribution suggested that small pieces could have separated or that its surface was shedding more rapidly than before. Observations from the solar and heliospheric observatory hinted at streaks of dust trailing behind the nucleus, faint and short-lived, but present enough to draw attention. All these signs, the volatile release patterns, the brightness fluctuations, the irregular tail, the spectral anomalies painted a picture of an object that was not steady, not calm, not typical. It behaved like something old, fragile, and unpredictable, shaped by environments no human instrument had ever seen. Its every shift, every flicker, every burst of activity added to its growing mystique. This unpredictability became one of the central reasons scientists took special interest in 3I Atlas. It wasn't just another interstellar visitor. It was behaving in ways that seemed almost reactive, as though it responded to sunlight with a kind of ancient volatility. And because its closest approach to the Sun coincided so closely with the most powerful solar flare of 2025, its unusual behavior only deepened the temptation to wonder whether something more than coincidence was at play as winter settled across the United States. In early 2025, the Sun entered the peak of its natural rhythm, a phase known as the solar maximum. Every 11 years, give or take, our star shifts from a calm, steady temperament into a more active and expressive state, filled with swirling magnetic tensions, sunspots that bloom like dark islands across its surface, and bursts of energy that ripple through the solar system. For most people, these changes go unnoticed, because the Sun still rises and sets in the same familiar rhythm. But for scientists, for satellite operators, for radio technicians, and for anyone who has ever watched the shimmering curtains of an aurora dance across the northern sky, the solar maximum is a reminder that even the most constant part of our daily lives is capable of awe-inspiring power. By January of that year, the Sun had already produced several strong flares, brief eruptions of energy that radiate through space, like the cosmic equivalent of a lightning strike. Most of these flares were moderate, classified in the lower ranges of the X scale, which measures the intensity of the Sun's most energetic outbursts. But as the month unfolded, instruments at NASA, NOAA, and observatories across the US began to record increasingly complex magnetic activity. Sunspots grew larger, their shapes twisted into patterns that hinted at deep, tangled forces beneath the solar surface. Solar physicists who spent their careers reading these patterns could see that the stage was being set for something far more dramatic. Then came the day that would mark the strongest solar flare of 2025. The event unfolded over the course of hours, though the flare itself erupted in an instant. On that morning, the sun showcased a sunspot region so large it could be seen even through proper solar filters by amateur observers in states like Texas, California, Colorado, and Florida. Images from the Solar Dynamics Observatory revealed a sprawling magnetic complex, loops of plasma arching gracefully above the surface, glowing in wavelengths invisible to the human eye, but radiant in ultraviolet imaging. These loops looked peaceful at a distance, like luminous strands of silk suspended in slow motion. Yet beneath that beauty, immense magnetic stresses were building. Magnetic fields on the sun behave differently from anything found on Earth. They twist, stretch, and interlock in ways that seem almost alive. When these fields intertwine too tightly, they store energy the way a wound-up spring stores tension. And when the stress becomes too great, the magnetic fields snap and reconfigure, releasing massive bursts of energy into space. This process is the engine behind a solar flare. It is not a slow release, but an abrupt, explosive event, occurring in a brilliant flash that can outshine the entire solar surface in certain wavelengths. As scientists monitored the sun that day, they noticed a rapid escalation of magnetic shear, a sign that the stored tension was nearing its breaking point. Satellite monitors detecting X-ray emissions began to climb. On screens inside NOAA's Space Weather Prediction Center in Boulder, Colorado, graphs rose sharply, and alarms signaled the onset of a major event. Around the same time, the GOES satellites orbiting Earth detected intense spikes in radiation. Within seconds, it became clear the sun had released an X-class flare. And not just any X-class flare, but one of the most powerful of the entire cycle. For astronomers studying 3I Atlas, the timing was startling. Only days earlier, the interstellar object had made its closest approach to the sun, briefly entering the region where the solar corona, the sun's outer atmosphere, extends into space like an invisible halo. The coincidence caused eyebrows to rise in quiet labs across the US. But for the solar physicists whose lives revolve around monitoring these cycles, the flare was expected, if not in timing, then at least in probability. Solar maximum is a period of heightened drama. Flares, coronal mass ejections, plasma storms, they all become more frequent, more intense, and more unpredictable. The flare of January 2025 was a powerful reminder of this. In ultraviolet wavelengths, the eruption appeared as a flash of white-hot brilliance. Enormous loops of plasma surged outward, glowing with temperatures exceeding millions of degrees. Shockwaves rippled across the solar surface, disturbing nearby magnetic structures and triggering additional bursts of activity. The event was captured from multiple angles by satellites, from ground-based observatories, and even from amateur astrophotographers, who just happened to be recording the sun that day. The effects rippled outward toward Earth. High-frequency radio communications in parts of the US experienced brief interruptions. Pilots flying polar routes received alerts advising them of potential communication blackouts. The auroras intensified, painting the skies of northern states like Montana, North Dakota, and Minnesota with green and violet arcs of light. In some places, the glow stretched farther south than usual, delighting sky watchers and confusing those who had never seen the northern lights outside of winter vacations in Alaska. Scientists studied the flare carefully. They traced its origins to a region where two large magnetic fields opposed one another, like two currents of water pushing against each other in a narrow channel. The buildup had been visible for days. The eruption, though dramatic, was not unprecedented. What made this flare stand out was its magnitude in comparison to others that year. It was strong, fast, and energetic enough to generate interest across scientific communities far beyond the usual circle of solar physicists. This was also the moment when public fascination spiked. Because 3I Atlas had recently passed through the inner solar system, social media, news outlets, and even casual conversations began to link the two events. People wondered aloud whether the timing was too close to be coincidence. After all, how often does an interstellar object sweep near the sun just before a major flare occurs? The curiosity was understandable. It spoke to a deeper, almost instinctive human desire to find patterns, even cosmic ones. Many Americans, hearing about both events in the same news cycle, felt drawn into the story as though the universe had suddenly become more active, more connected, more dramatic. Meanwhile, scientists maintained a calm, methodical approach. They examined data from magnetograms, reconstructed the magnetic field topologies, analyzed the flare's particle emissions, and mapped the evolution of the active region. Nothing in the data suggested an external trigger, but the timing, undeniably striking, invited exploration. Researchers tracked the trajectory of 3I Atlas and calculated how close it came to regions of solar influence. They looked for any disturbances in solar wind measurements, any anomalies in the corona, any signatures that might indicate interaction. The conclusion remained scientific and measured. The sun was behaving as it always does during solar maximum, driven by forces deep within its own magnetic heart. Still, the interest surrounding the flare and its connection to the interstellar visitor created a sense of narrative in the minds of many, an unfolding cosmic chapter, happening in real time, tying human curiosity to the ancient rhythm of our star, and the rare appearance of a traveler from beyond it. When the strongest solar flare of 2025 erupted just days after 3I Atlas swept past the sun, a wave of curiosity rippled through both the scientific community and the public. The timing felt uncanny. It was the kind of coincidence that makes the human mind pause, lean back, and wonder if the universe had whispered a secret through the alignment of events. After all, interstellar objects are extremely rare. Solar flares of that intensity are rare. To have them occur so close together in time felt almost poetic, as if the cosmos had coordinated a moment meant to spark imagination. But imagination alone is not enough for science. And so the question was asked, carefully, quietly, without assumption: could an interstellar object actually trigger a solar flare? The idea itself is intriguing. It paints a dramatic picture of a visitor from deep space brushing past the sun, disturbing its fiery atmosphere and provoking a burst of energy that spreads across the solar system. The image is cinematic and mythic, the kind of scenario that captures attention instantly. But to understand whether such a thing is even possible, one must drift into the physics of the sun and consider how delicate or how resilient this enormous star actually is. The sun is not a passive body floating gently in space. It is a roaring sphere of plasma stretching more than 860,000 miles across, containing over 99% of the mass of the entire solar system. It generates magnetic fields so powerful they can twist themselves into knots. It produces currents of plasma that surge and swirl with almost unimaginable energy. Every second, it emits more power than all human civilizations have consumed in their entire history. An object like 3I Atlas, even if it were enormous by comet standards, is still essentially a speck of dust compared to the sun's massive scale. Yet the question persists. Because being small does not automatically mean being irrelevant. Nature is full of examples where tiny disturbances create large effects. A seed can become a forest. A grain of dust can seed a raindrop. A small imbalance can trigger a cascade. So the question naturally becomes, could a small interstellar object create even a tiny disturbance in the solar environment that leads to something larger? To explore this, scientists began with the most straightforward possibility: gravitational influence. Could 3I Atlas, moving along its hyperbolic path, have tugged on the sun in some way, even minutely? The answer, grounded in physics, is gentle and clear. The gravitational pull of a comet-sized object is negligible compared to the sun's mass. It is like a single snowflake drifting past the base of a mountain. It does not shift the mountain's weight, nor does it create tremors in the rock beneath. The sun's gravitational field is so dominant that 3I Atlas traveled through it like a grain of sand falling past the surface of an ocean. If gravitational influence was not a realistic mechanism, the next possibility was physical interaction. Could the object, or the gases it released, have touched the solar atmosphere, disturbing magnetic fields there? Scientists examined the trajectory of 3I Atlas with careful calculations. Its closest approach, while near the Sun in astronomical terms, was still millions of miles from the regions where solar flares originate. Flares are born deep within the Sun's magnetic structures, twisted, compressed, and buried beneath layers of plasma far thicker than anything an asteroid could pass through. Even if 3I Atlas had plunged directly into the Sun's corona, it would have vaporized instantly, leaving no chance for a controlled or targeted disturbance of magnetic fields. Still, scientists did not stop there. They explored another possibility: electromagnetic influence. Interstellar objects can carry charged particles. They shed dust and gas that interact with solar wind. Could these interactions, even faintly, have altered the behavior of the Sun's magnetic environment? The answer required careful modeling. Solar winds themselves are vast rivers of charged particles flowing outward from the Sun at hundreds of miles per second. The small plume of gas from 3I Atlas, while interesting, was insignificant compared to the sheer volume and force of the solar wind. Even released gases scattered almost immediately into the Sun's surrounding plasma environment, diluted into the immensity of space. As scientists continued to explore the question, they also examined the timing itself. The Sun had already been building magnetic tension for weeks. The sunspot responsible for the flare did not appear suddenly. It had been growing, developing complexity, and twisting its magnetic fields long before 3I Atlas arrived in the area. The flare was the culmination of a long, natural process within the Sun, not the result of an outside trigger. And yet, even as the scientific analysis leaned overwhelmingly toward coincidence, the curiosity remained understandable. Humans are pattern-seeking beings. We notice alignments, parallels, and synchronous moments. When the rare arrival of an interstellar object happens just before a major solar event, it feels meaningful, even if the meaning is not physical. It becomes a story the universe tells us, not through causation, but through timing, juxtaposition, and wonder. Scientists, too, are not immune to this sense of wonder. Many of them, after analyzing all the data, after confirming that the Sun acted on its own, still spoke quietly about how extraordinary the coincidence was. They marveled at how two rare events could unfold in such proximity. They acknowledged that while the physical mechanisms did not support any connection, the poetic symmetry of the moment was difficult to ignore. Even in scientific circles, the question continued to spark discussions because it offered a chance to explore the limits of what the Sun responds to. It allowed researchers to reflect on how powerful solar flares truly are, and how they originate from deep internal processes far beyond the reach of small objects. It invited deeper analysis of solar magnetic behavior, improving models, refining predictions, and fueling a broader understanding of stellar dynamics. And in the broader public imagination, the idea of an interstellar visitor stirring the Sun created a sense of cosmic drama, a feeling that the universe is alive with hidden interactions. It inspired conversations, encouraged people to learn about solar physics, and brought attention to the rare and delicate dance of objects moving through our solar system. It sparked curiosity not just about 3I Atlas, but about the Sun itself, about the galaxy, about how events unfold on scales both massive and microscopic. In the end, the question of whether 3I Atlas could trigger a solar flare opened a doorway into deeper understanding. It allowed scientists and the public alike to reflect on the nature of cause and coincidence, power and fragility, scale and insignificance, and the quiet beauty found in asking how everything connects across the immeasurable expanse of space. In the quiet moments that follow great discoveries, there is always a question that lingers in the background, drifting like a thin veil of mist across the landscape of human thought. What does the universe want us to understand? When an interstellar object like 3I Atlas passes through our solar system, it is more than just a visitor. It is a message written in the physics of motion, in the chemistry of cosmic dust, in the path traced across billions of miles. It is a reminder that our solar system is not isolated. It breathes, it exchanges, it interacts with the wider galaxy. And nestled within that reminder is a deeper invitation to consider our place in a cosmos filled with countless worlds. Countless trajectories, countless unknowns. The study of interstellar objects is still in its infancy. Only a handful have been observed passing through our neighborhood, and each one has carried its own distinct personality. Oumuamua, with its enigmatic shape and puzzling acceleration. Borisov, with its familiar yet foreign cometary behavior. And now, 3I Atlas, adding its signature to this unfolding catalog of cosmic wanderers. With each one, scientists gather new data and refine new theories, slowly piecing together a tapestry of interstellar chemistry and physics that reaches far beyond anything the planets of our solar system can teach us. Alone, one of the most striking realizations born from these discoveries is the sheer vastness of interstellar space and the resilience of objects that travel through it. These objects journey across unimaginable distances, light years upon light years, surviving radiation, collisions, temperature extremes, and isolation. They drift through regions where stars are too far away to be seen as more than faint glimmers. They pass through clouds of gas, through regions shaped by ancient supernova, through the gravitational tides of the galactic disk. And yet, by the time they arrive in our solar system, they still carry the chemical signatures of the worlds they once belonged to. This resilience raises profound questions about how material moves through the galaxy. It suggests that planetary systems constantly exchange debris, trading fragments of their origins like cosmic postcards drifting across millions of years. In the distant past, the early solar system might have been seeded by interstellar material from other stars, and in turn, fragments from our solar system might now be traveling through space, carrying traces of Earth's early chemical history to places we will never see. Scientists studying 3I Atlas approach it with this understanding. Every grain of dust released from its surface, every trace of gas detected in its spectrum, every measurement of its speed, rotation, or composition serves as a clue. These clues help reconstruct not only the object's present state, but also the environment where it was formed. Was it born around a young star, where turbulence and collisions are common? Was it ejected from a stable system through gravitational instability? Was it shaped by a violent encounter with another object? Each possibility opens up a different narrative, a different cosmic history. As 3 Atlas traveled deeper into the inner solar system, telescopes across the world began studying it with precision. Spectroscopic instruments examine the light it reflected, breaking it into colors and wavelengths that reveal molecular fingerprints. Some wavelengths hinted at carbon-rich material, while others suggested a mix of volatiles that do not perfectly match any known solar system object. This alone is significant. It means that 3I Atlas carries a chemistry shaped by another star, another environment, another era. It is like holding a relic from a different civilization, one that existed long before humans walked the earth. Perhaps before Earth itself had fully formed. This unique chemistry allows scientists to explore deeper questions. How common are organic molecules beyond our solar system? How often do other stars produce comets or asteroids similar to those we are familiar with? Does the galaxy share a unified chemical language, or do planetary systems develop dramatically different compositions based on the details of their formation? By studying objects like 3I Atlas, researchers hope to map out the diversity of materials that populate the Milky Way. Such knowledge brings us closer to understanding how planets form, how they evolve, and even how they might support life beyond chemistry and origin. 3I Atlas offers insights into the mechanics of interstellar travel itself. Objects that cross the vast distances between stars are not merely drifting. They are subject to gravitational deflections from stars, dark matter, and molecular clouds. They move through regions where magnetic fields twist and pull at charged dust. Over time, these forces sculpt their paths into complex trajectories that only appear simple once they reach a star system like ours. Mapping these trajectories helps scientists model how interstellar debris evolves across billions of years. It helps determine how often objects like these should appear, how fast they move, and how likely they are to intersect with solar systems like ours. These insights have broader implications. If interstellar objects pass through solar systems more frequently than once believed, then each passage represents an opportunity for material exchange. Fragments of worlds could collide with planets, potentially delivering organic molecules or water to young, forming surfaces. This deepens the possibility that the ingredients of life may not be confined to individual star systems, but may be shared across the galaxy. It paints a picture of life as a potential consequence of cosmic connectivity, rather than an isolated event. When scientists analyze 3I Atlas, they also consider the technological potential of understanding interstellar trajectories. As humanity begins imagining its own future beyond the solar system, studying natural interstellar travelers becomes a kind of blueprint. These objects have already accomplished what humanity has not yet achieved, traveling between stars, surviving the journey, and arriving carrying meaningful information. By observing how they move, how they withstand cosmic conditions, and how their materials remain intact, researchers gain insight into what future spacecraft might require for true interstellar exploration. In many ways, 3I Atlas is both student and teacher. It studies our sun as it passes, absorbing its heat, reacting to its radiation, shedding particles that reveal its internal structure, and at the same time, it teaches us about environments far beyond our reach. It is an ambassador from another star system, shaped by distant physics, carrying the echoes of a world we may never know. It moves silently through space, past planets, past orbits, past everything familiar to us. And as we watch it from Earth, through the stillness of night, through the lens of telescopes, through the quiet hum of observatories, we begin to understand how much more there is to learn, how wide the universe truly is, and how small we are in the presence of these interstellar wonders. There is a quiet moment in every scientific investigation when the data appears to form a pattern, when the timing of two events seems too close, too precise, too elegantly aligned to be the product of chance alone. It is in those moments that the human mind feels an almost irresistible pull toward connection. We are pattern seekers by nature, drawn to relationships between events, like moths to a soft source of light. When 3I Atlas passed through the inner solar system, and, not long after, the Sun released the largest solar flare of 2025, this pull became palpable. People wondered whether these two cosmic events were somehow intertwined, whether the interstellar visitor might have nudged, disturbed, or provoked the Sun into its sudden outburst. And beneath that curiosity lies a deeper question about how we understand the universe itself. In the calm of nighttime observatories, where data scrolls across screens and scientists speak in quiet tones out of habit rather than necessity, these questions arise with the same softness that permeates the air. Correlation, the overlapping of events in time, can be persuasive, but causation, the actual chain of physical mechanisms linking one event to another, requires far more than timing. It requires evidence, energy transfer, a clear and measurable influence. Without these, two events occurring close together remain just that, close together, but independent. In everyday life, it is easy to confuse correlation with causation because our minds evolved to make quick connections. If someone eats a new food and becomes ill an hour later, the instinctive conclusion is that the food was the cause. If one day is cloudy and cooler than usual, people might say the weather is changing for the season. Our brains are wired to find meaning in proximity, to weave stories from clusters of events. This helped early humans survive in a world filled with dangers and uncertainties. It allowed our ancestors to recognize patterns in animal behavior, weather changes, and the movement of stars. But in the vast stage of cosmic physics, patterns are not always meaningful. Events can overlap in time without touching each other in any physical sense. They can appear aligned simply because the universe contains more activity than our minds are designed to process. When a solar flare erupts shortly after an interstellar object passes near the Sun, the timing may spark wonder, but it does not necessarily signal cause. The Sun is a restless, magnetic, dynamic sphere of plasma undergoing constant changes. It has its own cycles, its own internal tensions. its own mood shaped by billions of tons of swirling incandescent gas. To understand the difference between correlation and causation in cosmic events, one must imagine the Sun as a system governed by internal processes far more powerful than anything an object like 3I Atlas could generate. Solar flares are the result of magnetic reconnection process in which magnetic field lines twist, snap, and reconfigure themselves, releasing enormous amounts of energy. These magnetic structures are driven by the Sun's rotation, convection, and deeply rooted plasma flows. They rise from layers far beneath the surface and unfold over weeks, sometimes months. By the time a flare erupts, the energy that fuels it has already been stored in these tangled magnetic fields long before the flare becomes visible. If 3I Atlas were to exert any significant influence on the Sun, it would need to interact with these magnetic fields in a measurable way. But the Sun is unimaginably massive, and its magnetic power dwarfs anything the interstellar visitor could carry. The energy released by a strong solar flare is equivalent to billions of nuclear bombs detonating simultaneously. In comparison, 3I Atlas, though a fascinating object, is tiny. It is a guest in a system dominated by forces it cannot meaningfully alter. Scientists understand this distinction, and they teach it carefully, not to dismiss curiosity, but to anchor it in evidence. When researchers study the timing of cosmic events, they are trained to look for mechanisms, not coincidences. They comb through data searching for measurable influences, gravitational perturbations, electromagnetic signatures, plasma interactions. If none are found, the events remain unconnected, despite the allure of their overlapping timelines. The interplay between correlation and causation also shapes how scientists communicate with the public. When something extraordinary happens in the sky, people naturally seek meaning. They want narratives, explanations that fit into a coherent sequence. This is part of the beauty of human thought. We are storytellers, always seeking to place ourselves within the unfolding drama of the cosmos. But science, at its heart, is about gently peeling away assumptions until only the evidence remains. It asks us to look closely, to think slowly, to allow the truth to reveal itself through data rather than desire. There is also something deeply human in imagining the universe as interconnected. For centuries, people believed that comets brought change, plague, war, revolution, or transformation. These beliefs were not rooted in science, but in the emotional power of celestial events. A bright streak across the sky was a disruption, a sign, a symbol. And even today, despite our knowledge, a trace of that old instinct persists. When an interstellar object enters the solar system, it captivates us in ways few phenomena can. It feels significant simply because it is rare, foreign, and mysterious. But the universe moves according to physics, not symbolism. Its beauty lies in the consistency of its laws, in the harmony of cause and effect, in the way energy flows through systems that evolve across millions of years. When two events occur close together, it may awaken our sense of wonder, but that wonder must be guided by reason. Understanding this balance between curiosity and discipline, between imagination and evidence, is part of what makes astronomy such a uniquely profound science. In the end, the timing of 3I Atlas and the great solar flare of 2025 invites us not to assume a causal link, but to reflect on the nature of coincidence in a universe filled with movement, cycles, and events unfolding on scales far beyond human experience. It teaches us how to navigate the space between what seems meaningful and what is physically true, reminding us that the cosmos is vast enough for coincidences to occur without intention or influence. And within that vastness, our task as observers is to approach each event with both awe and clarity, allowing ourselves to feel the wonder while still pursuing the evidence that leads to understanding. When the journey of 3I Atlas through our solar system finally began to fade from telescopes and drift beyond the reaches of our measuring instruments, what remained was not simply a collection of data points or orbital graphs. In the quiet moments between measurements, some scientists found themselves reflecting on the philosophical weight of what they were studying. To look at 3I Atlas was to look into the memory of another world, a place that might have had planets, oceans, and perhaps even organic chemistry capable of producing life. Some light years away, that parent system might have collapsed or drifted apart, leaving only this fragment to wander, and now, for a brief time, it had come here to our sun, our skies, our instruments offering a momentary glimpse into the immense network of cosmic history connecting all things. It was a reminder that interstellar space is not empty, but filled with relics of creation, silent and endless, carrying stories that began before Earth had cooled, before life had stirred in its ancient seas, before humanity had learned to look up and wonder in the long nights of observation. When the hum of cooling systems filled the silence of observatories and screens glowed faintly with streaming data, a strange unease began to settle among the astronomers studying 3I Atlas. It wasn't fear in the traditional sense, no threat loomed from the heavens, no danger of collision or catastrophe. Rather, it was a quiet, intellectual disquiet, the kind that seeps in when the universe refuses to behave according to its rules. Every new dataset that arrived only deepened that silence, a realization forming beneath the scientific calm. Something about this interstellar visitor was defying comprehension, and it wasn't just breaking the models, it was bending the very expectations of natural law. For generations, astronomy had been an act of confidence in predictability. Gravity, light, and chemistry all followed patterns that, once understood, could be applied across the cosmos. Stars obeyed the equations of fusion, planets danced to the same mathematical rhythms that guided Earth, and comets, though unpredictable in brightness, always followed certain thermodynamic rules. But 3 Atlas began to whisper that there were cracks in that order, small irregularities that couldn't be dismissed as noise or error. As its orbit shifted slightly in ways unaccounted for by known physics, as its surface emitted light and heat in conflicting cycles, astronomers began to feel that they were staring not just at an anomaly, but at a messenger from a deeper layer of reality, something that hinted at structures of matter and energy, yet undiscovered. The fear grew not from what they saw, but from what they could not explain. Late at night, in data centers, researchers stared at columns of numbers that resisted interpretation. The usual confidence that the next equation would bring clarity was replaced by a subtle humility, an awareness that perhaps the tools of their trade were insufficient. Discussions among senior scientists turned philosophical. Some suggested that 3I Atlas might be composed of exotic ices materials that behave differently under radiation due to unfamiliar molecular bonds. Others wondered if its irregular acceleration could be explained by the release of gases interacting with magnetic fields in ways that standard models did not yet account for. But every hypothesis seemed to solve one mystery only by creating another. At NASA's Jet Propulsion Laboratory, analysts ran simulation after simulation. Each time, the models diverged from reality. The comet's trajectory seemed to contain a faint rhythm, as if guided by pulses invisible to ordinary observation. Its spin rate, deduced from light curve analysis, would subtly fluctuate, speeding up for days, then slowing to near stasis before resuming. The pattern repeated with uncanny precision, yet no physical process could explain it. These oscillations were too smooth for random fragmentation, too stable for mechanical tumbling. Some likened it to a heartbeat, an internal metronome echoing through the void. The phrase caught on informally among the research teams, the heartbeat of 3I. It wasn't meant to suggest anything alive, but the metaphor lingered in the air, unspoken, yet impossible to ignore. There was a certain weight in knowing that one was witnessing something never before observed. The astronomers who had studied Oumuamua and Borisov had faced mystery too, but theirs had been accompanied by discovery, a sense that each question led to new knowledge. With 3I Atlas, however, the questions multiplied without resolution. Every answer dissolved into uncertainty. The comet's energy output made no thermal sense. Its reflectivity changed in measurable yet meaningless ways, and its chemical composition refused to remain constant. Instruments that had been trusted for decades returned readings that were internally consistent, but cosmically absurd. It was as if the universe had chosen this one object to mock the precision of human understanding. Some of the younger astronomers found it thrilling. a glimpse into the unknown frontier that had drawn them to science in the first place. But for the veterans, those who had spent lifetimes refining equations and verifying constants, the uncertainty was quietly unsettling. In private moments, they spoke about it as if describing a dream they couldn't interpret. One astrophysicist at Mauna Kea compared it to listening to a familiar symphony suddenly played in a new key, recognizable, yet wrong in a way that made the entire composition feel alien. Another described it as watching gravity lie. In conference rooms and video calls, discussions grew more abstract. Could 3I Atlas be composed of material that reacts to solar radiation in non-linear ways? Could it have internal magnetic structures inherited from its parent system that respond differently to the sun's electromagnetic field? The question spiraled outward, touching the edges of known physics. A few theorists dared to suggest that perhaps interstellar objects like this were not bound by the same constants that govern our corner of the galaxy, that the chemistry and energy states of matter could vary subtly between star systems, shaped by differences in radiation or cosmic background fields. It was speculation on the edge of reason, yet no one could fully dismiss it. In those final observations, scientists found both wonder and a hint of disquiet. The interstellar traveler had come closer to the sun than most comets dare, faced its radiance, and revealed phenomena that pushed the boundaries of understanding. It had endured in ways no one thought possible, carrying the physics of another world into the light of ours. And then it had gone, leaving behind only a memory etched into the instruments that watched its passage, and into the minds of those who had followed its journey from the moment it appeared at the edge of the stars. The story of 3I Atlas stands as one of the most extraordinary chapters in our ongoing exploration of the cosmos. It began as a faint point of light, an anonymous traveler entering our solar system from the cold depths between the stars. But as it revealed its true nature, it became far more than a comet. It became a cosmic messenger. Every observation, every anomaly, every flicker of light challenged the boundaries of human understanding. Scientists saw in it the fingerprints of processes that began light years away, in environments utterly unlike our own, shaped by conditions that may never exist again in this system. 3I Atlas defied expectation from the moment of its detection. It moved unlike typical comets, rotated with strange precision, and held a composition that spoke of unfamiliar chemistry. As it approached the sun, it refused to obey the familiar laws of thermal decay. Instead, it brightened, pulsed, divided, and endured in defiance of destruction. It carried within it the memory of another star's light, another world's dust, and through its passage, it offered Earth a fleeting glimpse into the grand continuity of the universe, a reminder that creation and motion transcend any single system. The encounter changed more than data, it changed perspective. It forced humanity to look outward again, to remember that our sun is but one of countless others, and that space between the stars is not empty, but alive with travelers, fragments, and memories from other beginnings. The journey of 3I Atlas is a symbol of cosmic persistence, of the strange resilience of matter shaped beyond our understanding, and of how the unknown continues to move silently among us, waiting to be seen. Though it now drifts beyond the reach of our instruments, fading back into the black expanse from which it came, its legacy endures in the particles it left behind, in the data that continues to be studied, and in the awe it inspired across the world. The light of 3I Atlas may have vanished, but its story remains, a bridge between the stars and the human mind that dared to follow it into the fire of the sun and beyond.